This video showcases a comprehensive timeline of cellular security research conducted by the KAIST Systems Security Lab. From 2014 to 2025, we have consistently uncovered critical vulnerabilities in cellular implementations and specifications, shaping a more secure future for cellular communication. We begin Section 1 with attacks using fake base stations and fake UEs. This demo shows a control plane attack from our IEEE S&P 2019 paper. Touching the untouchables. The attacker first captures the victim's IMSI by impersonating a legitimate LTE base station. Then, a malicious attach reject message is injected into the unauthenticated control plane. The victim's device immediately loses its connection and enters a persistent denial of service state. This research, CI testing, presented at ACM CCS 2025, explores systematic testing of context integrity violations in LTE core networks. The attack targets an implementation flaw where certain message combinations are accepted by the core network without proper authentication. By spoofing the victim's identity, the attacker sends a specific sequence of unauthenticated messages to the MME. As shown in the demo, even after the victim toggles airplane mode, the device fails to reattach to the network because the core network context is corrupted. This is LL-Fuzz, an over-the-air dynamic testing framework for cellular baseband lower layers, presented at UScenic Security 2025. LL-Fuzz successfully identified 11 critical memory corruption vulnerabilities in commercial basebands. Upon receiving the packet, a memory corruption occurs, leading to an immediate crash of the baseband processor. As the baseband process terminates, the device completely loses cellular connectivity, as shown on the screen. This video demonstrates the end-to-end operation of an SMS blaster, mimicking real-world cellular fraud techniques. The process begins by activating an LTE fake base station to attract nearby target devices. Next, a 2G fake base station is launched, setting the stage for a protocol downgrade attack. Through connection hijacking, the victim's device is forcibly handed over from LTE to the insecure 2G cell. Once the device is attached to the 2G rogue cell, the FBS injects spoofed SMS messages without any integrity checks. The victim receives the fraudulent message, illustrating the critical vulnerability of legacy protocol fallback. The rogue base station first modifies SIB1 to include scheduling information for a fake alert. Once the device detects the update, it proceeds to read the malicious SIB12 containing the alert. Without any integrity check, the device immediately displays the forged emergency message as well as alarm sound. Section 2 focuses on privacy and location tracking. We present LTE sniffer, location tracking, video fingerprinting, and femtocell war driving. This video demonstrates LTE sniffer, an open-source tool for SNFFing LTE uplink traffic, presented at WISEC 2023. Phase 1. To identify the victim's TMSI, the attacker places multiple calls every 15 seconds to trigger paging messages. By observing the recurring TMSI value across these calls, the attacker uniquely identifies the victim's temporary identity. In Phase 2, the tool maps the identified TMSI to the victim's RNTI by sniffing the RRC connection setup process. Finally, using the mapped RNTI, LTE sniffer successfully decodes and sniffs the victim's uplink. This video demonstrates a video identification attack in LTE networks, presented at UScenic Security 2022. We have 3 devices here. While the left phone streams a cricket match, the victim in the center begins watching a Michael Jackson music video. By sniffing the broadcasted DCI downlink control information, we can identify the specific device streaming the target video by matching traffic patterns. Once the victim is identified, the attacker uses a rogue base station to force the target device to attach to its malicious network. After the forced attachment, the attacker can execute various payloads. Here, we demonstrate sending a fake emergency alert to the victim's device. Beyond fake alerts, this control allows for more severe attacks, such as pushing malware. This video demonstrates the core concepts of our ACM Mobicom paper, enabling physical localization of uncooperative cellular devices. The demonstration was filmed in collaboration with Professor Seong-Uk Park's laboratory. The system operates on a dual antenna principal downlink antenna for continuously collecting DCIs, directional uplink antenna for localizing uplink signal. By analyzing this DCI, the system identifies exactly when and on which frequency the victim device will transmit its uplink signal. We then synchronize this data with a directional antenna. Because of its high directivity, the LTE sniffer will only detect the target's uplink signal when the antenna is pointed precisely at the victim's location. This section presents a multi-device tracking system produced by Professor Seong-Uk Park's laboratory. The technical details are published in IEEE Transactions on Instrumentation and Measurement, titled Passive 3D User Equipment Tracking Using LTE Uplink Signals. By applying advanced direction of arrival DOA estimation, the system enables simultaneous 3D tracking of multiple uncooperative devices. This allows for high-precision localization of various targets within a single monitoring scan, significantly enhancing tracking efficiency. Here is a real-world demonstration in Cheonhodong, Seoul, in collaboration with Korean police. We deployed this setup to locate a device used in an actual voice phishing operation. As the antenna rotates, a clear uplink signal appears on the sniffer when aligned with the target. This successfully pinpoints the exact hideout in a dense urban alleyway. A femtocell is a small cellular base station designed for indoor use or dead zones. When active, user A's device connects to the femtocell, and the wireless communication between them is encrypted. The call is temporarily decrypted within the femtocell before being re-encrypted via IPsec to reach the core network. If an attacker gains root access through a vulnerability, they can intercept this briefly decrypted voice traffic. This device is a mobile eavesdropping tool created by connecting a rooted femtocell to a commercial hotspot and a battery. This is the exact setup used in the high-profile KT small payment fraud case. Let's proceed with the demonstration. We will now listen to the intercepted audio file.
저요. 소파에 앉아 있어요, 그냥.
알았어. 좀 더 다시 전화해봐.
네.
끊어. 알았어. 좀 더 다시 전화해봐.
네.
Section 3 covers signal manipulation and service exploitation, featuring charging bypass, signal overshadowing, and VoLTE caller ID spoofing. This research, titled Gaining Control of Cellular Traffic Accounting by Spurious TCP Retransmission, was presented at NDSS 2014. We demonstrate a free-riding attack that exploits a flaw in how carriers handle TCP retransmissions to bypass data accounting. By using a custom TCP tunneling proxy to manipulate headers, the attacker can disguise all regular data packets as non-billable retransmission. As the victim watches a high-definition video, the traffic is treated as lost packets being resent, allowing for free data usage. Consequently, the system only charges for 4.4 megabytes of data, even though the actual consumption exceeds 429 megabytes. This video demonstrates the signal overshadowing attack on LTE networks, presented at UCNIX Security 2019. Under normal conditions, the device maintains stable data connectivity and VoLTE voice services. The SIG over attack exploits the fact that broadcast signals from the base station are not authenticated, allowing malicious signals to overwrite legitimate ones. Specifically, the attacker injects a forged access barring message via SIB2, forcing the device to stop all network access attempts. Even after the attack stops, the victim device remains disconnected, resulting in a persistent denial of service. This research, Breaking and Fixing VoLTE Exploiting Hidden Data Channels and Misimplementations, was presented at ACM CCS 2015. We demonstrate a caller ID spoofing attack that exploits the lack of binding between a phone number and its cellular identity in the IMS network. Normally, a call correctly identifies the caller. Observe that while the actual caller's phone remains completely idle, the Kali receives a call appearing to be from that caller. This spoofed call is made possible by injecting malicious SIP messages, bypassing the carrier's identity verification process. Over the past decade, KAIST CISEC has identified hundreds of implementation bugs in major global vendors and dozens of design flaws in 3GPP and GSMA standards. Through responsible disclosure, we remain committed to building a more secure and private mobile ecosystem for the future. Thank you for watching.